Coulomb's law has to do with how strongly attracting or repelling two charged objects are. So if I have an object here and I have an object here, and this has a net positive charge and this has a net negative charge, I know that they're going to be attracted. Okay, so the direction of the mutual force, which we call the electrostatic force on them, is attractive. If these were both positive or both negative, they would repel each other. Okay, so the net electrostatic force on each, I shouldn't say net, the electrostatic force on each would be repelling. And that's true if they're positive, both, or negative, both, because similar charges repel. Okay. And it does not matter, by the way, how much charge there is on there for the direction. We know that similar charges of any magnitude will attract each other. Even if this is much more strongly charged than this one, Newton's third law says they're going to attract with the same force. Now, when we did gravitation, it was always attractive. So if this had mass and this had mass, the gravitational force would always be attractive. Charge is a little different in that these two charges can either attract or repel depending on their polarity. And the strength of the force is given by what we call Coulomb's law. And we call it the electrostatic force, and it's equal to, think of the gravitational force. Gravitational force is capital G, m1, m2 over r squared. Well, this r squared has to do with the fact that if we think of a field, a gravitational field, let's say that's a planet, the gravitational field is always in towards the planet. So if I put a mass in that field, it would be attracted. But these field lines get farther and farther and farther apart. And in fact, in 3 dimensions. So you could think of, if we think of a little shell right there, the gravitational field will be much stronger there than out here. And in fact, we think of the field being spread out in 2 dimensions on a 2-dimensional sphere, a 3-dimensional sphere, but the surface, and we think that field would be spread out over a greater and greater area on the farther out shields. A way to think of it here is if we think of a little patch right here of this planet, and we think of that coming out like this, goes out in 2 dimensions. So out here, that same field intensity would be spread out in 2 ways. That's where the r squared comes from. They call it inverse r squared relationship. So similarly, we're going to eventually get to electric fields that go out the same way. Okay, and if I put this charge in that electric field, again, that field out here would be significantly smaller, and it would go down as 1 over r squared. So this is another of those inverse r squared relationships. And intuitively, it would be related to the charge. Let me call this plus Q1, and let me call this minus Q2. It would be related to the magnitudes of the charge, Q1 and Q2, just like gravitational force related to M1 times M2. And there's going to be a constant out front, and that's called variously the Coulomb constant, electrostatic constant, but that K is a constant that relates these things. So it looks an awful lot like our force of gravity equation. The K is 8.99 times 10 to the 9th, and if we think of what the units would have to be, it would be Newton meters squared, Nm squared, divided by Coulomb squared. Okay? For AP Physics C, there's another way of showing what that K is. It's 1 over 4 pi epsilon, which is a epsilon 0, which is the free space permittivity. But we're not going to deal with that right now. Okay, so this is a big number. Remember, the gravitational constant was 10 to the negative 11, 6.67 times 10 to the negative 11. So this is a huge number. And in fact, electrostatic force is really strong. If you think of all the materials that we have, they're held together by electrostatic force, by attraction between atoms and electrons fitting into energy levels and linking things together. So if you, this board right here, this pen right here is mostly empty space. You've got all these protons and neutrons in the center, and you've got these electrons, and then you've got other atoms adjacent. It's mostly empty space, but the forces holding those things together are so strong, partly because of this electrostatic constant, or this Coulomb constant. Okay, that's really the concept of Coulomb's law. It's just like gravitation. There's one difference. I didn't draw this as a vector. I didn't draw this force as a vector in the equation. And that's because what I want you to do is use this to find the magnitude. Okay? I don't care if this is plus or minus. Use the absolute values of those things. Find out how strong that force is, then use your brain to figure out what direction. So, if I calculated, for example, that if I have a 6 microcoulomb charge here, and I have a 2 microcoulomb charge here, and I want to find out the force between them, I need the distance. This distance is, I'm going to say they're 0.1 meters apart. So to use my Coulomb's law, what I would do is Fe equals, and again, the magnitude of Fe, not going to worry about the direction just yet, is going to be, by the way, in my class, you can round that as 9 times 10 to the 9th. 9e9 times, let me get these, make that smaller, 6 microcoulombs, times 6 times 10 to the negative 6, that's micro, times 2 times 10 to the negative 6, divided by 0.1 squared. Okay, and I've got to get a calculator, but when we calculate that, we find 9 times 10 to the 9th times 6 times 10 to the negative 6 times 2 times 10 to the negative 6 equals, divided by 0.1 squared, and I end up with 1.08 times 10 to the 13th, so something's wrong there. It should be 10 to, I clearly hit something wrong. I'm not going to waste time on it. It should be something very small. 10 to the, this is about 10 to the 10th. This is about 10 to the negative 11th divided by 0.01 would be something larger than 1, but not significantly. 6 seconds. I think I had a, I missed a negative exponent somewhere. That's looking a little better. Time divided by 0.01. 10.8. Much better, much better. 10.8 newtons is the magnitude of the electrostatic force. Then we use our brains. Oh, positive, positive. The forces will be repelling. Same numbers. Okay? So we could actually use that to find the instantaneous acceleration on each of these if we knew the masses. Now, I'm going to set up the pith lab, the pith ball lab. This is a classic demonstration. I'm not going to actually demonstrate it. I'm just going to show you the math, where they hang two chargeable balls. Let me just put it over here. Two chargeable spheres, metallic spheres, down, and they charge them. And if they charge them with the same charge, what will happen is they will repel, and it'll end up looking like that. Okay. So the way we use this pith ball demonstration is we do a free body diagram. So if I do a free body diagram for this one, I've got mg, I've got tension, and I've got the electrostatic force. Same thing, but switched over here, just mirror image. If I can measure this angle, and if I know this distance between the centers of charge, point charges, so if I know that R, then what I can do is I can break up that tension vector into T sine theta, T cosine theta, Fe, and mg. And sometimes what they do, if these two are hanging from the exact same spot, you could use the length and theta to figure out the distance to the middle. So this R would be 2 times L times the sine of theta. It's just geometry. Or you could measure the R itself. Either way, what happens is we can now write an expression for the electrostatic force, K, Q1, Q2, over R squared. So there's a variety of variations on this. A standard thing is you know R, you know K. If these are the same charge, we could just write that as Q squared. So we could find Q by using this equilibrium. So mg divided by cosine theta would be T. T times sine theta would be electrostatic force. If we know R and K, we can find the charge. So that's a common experiment that uses Coulomb's law to determine the charge on two objects if it's equal charges. So that's Coulomb's law. That's one application, a very common application of Coulomb's law in AP physics classes. And in the next class, we'll start talking about electric fields and charge motion.